due to Williamson. And so it's called the P-canonical basis because in fact it only depends on P. It does not depend on the choice of the field K. It does not depend either on the choice of the Kac-Moody group. It's well, up to, does not really depend. I mean, one should be careful, but in a sense, it does not depend too much on the Kac-Moody group. And yes, so this is the P-canonical basis, and this is an interesting subject in representation theory. So this is what we can do in the presence of geometry, but we can try.
Excuse me, can you? Is there any relation to Kazhdan-Lusztig basis? In the first example, you just get Kazhdan-Lusztig basis, and here
yes. So
canonical basis. How is it related to that? Or?
So so first of all, the definition of parity complexes or of this basis doesn't require K to be of characteristic P. You can also do it over a field of characteristic 0, and if you do so, you recover these semi-simple complexes. So this is what happens. And if P is positive, then the elements in this P-canonical basis, they are linear combinations with positive coefficients. I mean, the coefficients in the Kazhdan-Lusztig basis are Laurent polynomials with positive coefficients, with non-negative coefficients. And if you can, so in here there is a parameter P, and so you can wonder what happens when P grows. And if you fix some element W and consider the corresponding element in the P-canonical basis, you can fix this W and let P go to infinity, and at some point this will stabilize to the usual Kazhdan-Lusztig element. So in particular, if W is finite, if it is a finite group, then if P is sufficiently large, the P-canonical basis is just the Kazhdan-Lusztig basis. So there are only finitely many prime numbers to consider. But, well, we don't really understand which, how far one should go for this stabilization. And if W is infinite, so you cannot find, so in general there is no P that works for all elements.
Even for finite type W, does it make sense for different P compare the transition matrix, or any evidence saying there are some positivity?
No, if you compare P-canonical basis for two different values of P, I don't think there is anything known. Yes, so there are results about comparing with the Kazhdan-Lusztig basis, but not for two different prime numbers. Yes, I don't think there is anything known, and I'm not sure we should expect anything. Okay, so that's what we can do for these crystallographic Coxeter groups, but one might want to go beyond that and consider general Coxeter systems. So the work I mentioned related to representation theory of relative groups, it worked in this setting of parity complexes. So it applied to crystallographic Coxeter systems. But now one might want to consider general Coxeter systems. And so there is, again, two versions of this, one older and one more recent version. So the older version is due to Zergel. And for that, we need to specify some representation of W, which satisfies some technical condition. So he should be a reflection faithful representation. So once again, I will not explain what this means, but this is a technical condition on the representation. Then one can consider the Zergel bimodules. And this gives so bimodules for this attached to this representation, and these Zögel bimodules are certain. So we already saw them in some talks. These are graded bimodules over the ring R, which is the symmetric algebra of the dual vector space. So this is a classical topic, and so it appeared explicitly in the talk by Zögel, and in some non-explicit way in the previous talk. In particular cases, and it was conjectured by Zögel and then it was recently proved by, so this is a theorem by Elias and Williamson, that for certain choices of V, so for appropriate choices of V over which leave over the real numbers, but well, so the representation they consider R over R, but it's not any representation over R. It's you need to satisfy some properties. Then the canonical basis is again the Casual-Gnostic basis. And this is a very interesting result because by previous work of Zögel, this implies the Casual-Gnostic positivity conjecture. Which says that the coefficients of the elements of the Casual-Gnostic basis expressed in the standard basis they are polynomials with non-negative coefficients. So that's one way to consider a categorification for any Coxeter system. Well, yes, I didn't say so, but reflection faithful representations they always exist. For any Coxeter system, you can always consider some reflection faithful representations over the real numbers that satisfies the condition considered by Elias and Williamson. So you have at least one category you can play with. But there are representations that naturally occur in nature, in problem representation related to representation theory, which are not reflection faithful. And so for these representations, the theory of Zögel bimodules at least is not available. And so there was a need for a generalization of this construction, and it was found some time ago by Elias and Williamson. And so in this case, one should specify some realization of the Coxeter system. So I'm working over a field, and so, well, you can also consider the theory over rings, but I want to focus on the case of rings, and I want to make all the standard technical assumptions in this subject that I will not recall. The part of the theory works for general realizations, but then if you want to have the whole package, you need some technical assumptions. And I assume that all these technical assumptions are satisfied. In this case, you can consider the Elias-Williamson diagrammatic category. So here again, I will not recall the definition. So the definition in this case is by generators and relations. And so you have a bunch of generators and a bunch of of relations, and in this way you get a monoidal category. And Elias and Williamson proved that it provides a categorification of the Hecke algebra in the sense that it satisfies the conditions that are still on the board here. And I will denote it by D of HW. And I will make a couple of remarks on this construction. So the first thing is that the last example, the version of Elias-Williamson, it recovers all the other ones as special cases. So the last example covers all the previous ones. So yes, so this is strictly more general than all the other cases. So this is the setting that we will really consider,
including p bases.
I'm sorry.
Including p bases.
Yes. And so these yes, this category still has some flavor of bimodules, in the sense that for Mn in this category, if you look at the space, so if you look at the sum, so the direct sum of the morphisms from M to all shifts of M, so in this diagrammatic category, this is naturally a graded R bimodule. Graded R bimodule with R defined as before. So part of the datum of realization is a vector space, and we take the symmetric algebra of the dual vector space as R. And well, because of this, one can kill. Well, just tensor with the trivial module for the left or the right action. Or right action. To get a category which, well, has now Hom spaces which are just R modules on the left or on the right, and to get categories that I will denote like the underline and the overline. If you kill the left action, I get the overline, and if I kill the right action, I get the underline. And so these categories are modular categories over the monoidal category, and they categorify now the Hecke algebra as a module over itself, either a left module or right module over itself. And this is a reasonable process because the Hom spaces, the morphism spaces, they are free as left modules and also free as right modules. So you don't, in a sense, you don't lose information by passing to these quotients. And third remark is that so a few years after Elias and Williamson found this definition, there was work by Noriyuki Abe which gives a realization of this category as a category of graded R bimodules with additional data. Category of graded R bimodules. So Abe's theory works essentially in the same generality as the version of Elias and Williamson. So if you don't like generators and relations, you can just take Abe's definition is just a certain category of graded R bimodules with some additional data. And so I can ask the question that will be answered in the rest of the talk, which is, can we get a categorical interpretation of I. And what is essentially the same.
Say something. What's the advantage of Abel's construction?
I'm sorry?
What's the advantage of this?
It's less abstract. It's just R by modules, and sometimes, so the construction by Elias and Williamson is so it's given by generators and relations. So it's really good if you want to construct a functor from the category to somewhere. But if for some reason you want to construct a functor from a category to their category, then this is not really adapted. And in this case, you might rather want to construct a functor with values in this incarnation. Because here you just need to specify some R by modules. So to have a way to produce R by modules. And this is, well, so I have already used this in some works. That's really useful. And yeah, so I can ask about categorical interpretation of I or of the image of the canonical basis under I. So in this casuistic story, we had two versions of the canonical basis. One of them has an interpretation in these terms. So there are various things you can try to do about the second one, but one stupid thing that we can do is just take the image and the I of the first basis and say, this is my replacement for the second basis. And you can ask, does this have a categorical interpretation in terms of these categorifications of the Hecke algebra? And yes, I don't have time to really explain why. So this might seem like a stupid thing to do, ask why one want to consider to categorify I. But so the motivation for this construction comes from this causal duality, which really does provide a categorical interpretation of this. So one way of interpreting it, at least, gives a categorification of this map. And yes, so and we wanted to consider, to see how far our methods could go in this direction. So to state the answer for this, I need to talk about the perversity structure. So in the case of crystallographic Coxeter systems and for some wise choices of realizations, the categorization that we consider can be described in terms of some category of sheaves. And a lot of the techniques that we use are based on this example, and we try to mimic the things that we like to do with sheaves in a more abstract setting. And so in particular, in sheaves we have a nice T-structure called the perverse T-structure, and it turns out that one can make sense of this perverse T-structure in for a general Elias-Williamson category. So we fix a realization H, and now we'll consider the corresponding category. And so the definition of I involves some minus sign. So it sends V to minus V inverse. And so this is an indication that if you want to categorify it, you should not work at the additive level because you will not, it will be difficult to realize this minus sign. And you should rather pass to the homotopy category where this minus 1 will just correspond to a shift of a common to a shift. So we work with triangulated categories now. And you will have three versions. Three categories we will work with. So first, the bi-covariant version, so BE of H W. This is the bounded homotopy category of the Elias-Williamson category. So this is a monoidal category. We call it bi-equivariant because in geometry it corresponds to sheaves on the group which are equivariant on both sides. Then we will have the right equivariant version, so which in geometry will correspond to sheaves which are equivariant only on the right. So this will be the homotopy category of the category D overline of HW, and this will be a right module over BE. And then there is the left equivariant version, which is the left module given by KB of D underline HW. And so these are these three categories. They are triangulated categories. So there is a homological shift, and they have also the shift coming from the parenthesis 1. So the shift in the internal to the category to the additive category. And one want to consider some combination of these, which we call the Tate twist, because in geometry it really corresponds to Tate twist. And it is the composition of internal shift by -1 followed by homological shift by 1. So in this, well, we will consider this in the three cases. And these categories are related by functors, well, some kind of forgetful functors. So the bi-equivalent version maps to the right equivalent version. I will denote this functor by 4. And it also maps to the left equivariant version just by the operation of passing from the R module to the tensor product with the trivial module. And in this generality, we have so the first. So one thing that we remarked with Pramodachar and Christian Weil is that the theory of Rouquet complexes can be developed in this generality as follows. So for S in S, we have complexes which I will denote by delta S and nabla S. So in geometry, it corresponds to standard object and co-standard object, to standard perverse sheaves and co-standard perverse sheaves. And these are exactly what the Rouquet complex is. So this BS is the element of the Elias-Williamson category attached to a simple reflection. So in this complex, it's in degree 0. This is in degree 1, and all the other terms in the complex are 0. And then the morphism is given by, well, what is denoted by this upper dot in the notation of Elias and Williamson. And for the co-standard object, you do essentially the same, but now you have BE shifted by -1, which is in degree -1. This is in degree 0, and now you have the lower dot morphism. So these are just some objects of some complexes which we consider in the homotopy category, so in the BE category, say. And so these are just complexes which are non-zero only in 2 degrees, either 0 and 1 or -1 and 0. And these are the building blocks for the Rouquet complexes. So I can state the first result that we use. So this is in the context of Zergel bimodule. This is due to Rouquet. Well, the construction is due to Rouquet, and then one of the properties that I will state is due to Lebiedinsky and Williamson. And in this generality, this is so part of this work with Achar and Weil. So I take W in my Weil group, and I take any reduced expression the objects. So I consider the objects in the homotopy category delta W, which I obtain by convolving just taking the monoidal product of the things associated to each of the simple reflection, and I do the same for the nabla version. And the first result is that this only depends on W up to isomorphism. So it doesn't depend on the choice of reduced expression, which is another way of stating that these objects satisfy the regulations. So that's the part which is due to Riche in the case of in the traditional case of Zögel bimodules. And the second part is the following: that we can so that these objects really behave as standard and co-standard objects in this theory. So we can describe morphisms from delta W. So from in the BE category from delta W to nabla Y with a shift by N, shift by M. And this will be, I think this is this shift. And this will be R to the M if W equals Y and M equals minus N is a non-negative even integer, and this will be 0 otherwise. So essentially, delta W only maps to nabla W. It cannot map to any other nabla Y.
So, is the homological degree somehow shifted? Because usually the non-vanishing would require M equals 0.
Yes, that's because this is not the shift which is T exact.
Oh, okay.
I will say so I will explain in a minute what is so there is the next result will be that these are really standard and co-standard objects in the heart of a certain structure, but the shift which is T exact is this shift here. So maybe I should not have erased this board, but it's too late anyway. And yeah, so these another way to see these, or to understand these objects, is that they give a categorification of the standard basis. Of the Hecke algebra. And so once I have these objects, I can state this theorem about the purpose T structure. So there exists a unique T structure on BE such that the non-positive part of the T structure is generated under extensions by objects of the form delta W, angles M brackets N with W in W, M an integer, and N a non-negative integer. So generated under extensions by that. By extensions in the sense of triangulated categories. And so that's the lower than 0 part, and the larger than 0 part is generated in the extensions by the nabla W's shifted by M, shifted by N, with W in W, M in Z, and N in Z less than 0. So So well, this description is exactly what happens for perverse sheaves on fact varieties, and we just try to mimic the construction. And the construction of this T-structure is again similar to the construction of the perverse T-structure. It's obtained by gluing. And so many of the results on perverse sheaves that, well, all the results that only depend on the theory of gluing, then they also hold here. And for any W in W, the standard and co-standard objects belong to the heart. So I'm supposed to finish in 5 minutes, right?
Yes.
Okay, so I'll try to do that. And as a corollary of this, we obtain that, we have the same for the right equivalent version and for the left equivalent version. And as a corollary, we obtain that the hearts are graded high. Well, the hearts on RE and LE are graded highest weight categories. And these delta objects are the standard objects, and the nabla objects are the co-standard objects. And so when we have a graded highest weight category, one can consider the tilting objects. So one can consider the tilting objects, so the indecomposable, the tilting objects in the heart. And they are classified by the indecomposable tilting objects are classified by the Val group, well, up to shift again. And in decomposable, I will denote them by T upper line W in RE and T underline W in LE. And so finally I can state causal duality. So causal duality will relate these categories for H to the categories for the dual realization. So we consider H and also the dual realization H star, so obtained by just replacing the vector space by its dual. And so we will consider RE of HW and LE of H star W. So that's why I explained both versions, because I want to take one version on one side and the other version on the other side. And in here I want to consider the objects obtained from the Hecke complexes by the four functor, the forgetful functor. The same for the nablas. And I have the image of the indecomposable object in the Elias-Williamson category. So I said that the indecomposable objects in the category are classified up to shift by the Val group. So I have an element BW and I consider its image in the category RE. And I also have T overline W, which is the indecomposable tilting object. And I have the same, similarly defined objects for the dual category, and I will denote them with a hat. No, this is underline. It's in the LE category, and so the tilting. And now I can state the theorem. the theorem, which is the main result of this work with Spitz and Pai, is that under a certain technical assumption that I will not explain, under a technical assumption, which, well, I will say just a few words about this technical assumption. There exists an equivalence of triangulated categories kappa from Re of each W to Le of each star W such that, so first kappa mixes the different shifts, so kappa composed with angles 1 is parenthesis 1 composed with kappa. Kappa of delta overline W is delta underline W hat. Kappa of nabla is nabla. Was the old thing? And kappa of it will exchange the objects B and T. So kappa of the overline W is T underline hat W, and kappa of T overline W is the underline W. And so this equivalence is a categorification of this operation I, in the sense that passing, so using the first two lines, you will see that passing through the Grotling group, you will get exactly this map I. And I don't have time for the comments, in particular to explain this assumption, but you are welcome to ask questions if you are interested.
So what happens to BE?
So,
I mean, is there an equivalence for
yes, yeah. Yes. So I've stated the version in the simplest form, relating this Re to Le. But in fact, in practice, we do construct a version for BE and obtain this as a corollary. But so in the construction for the bi-equivalent thing is similar to the Bezukhadnikov-Yun construction. So on the dual side, it will we'll have to consider some kind of free monatomic version of these categories BE, RE, and LE. And the construction of this free monatomic version is quite technical and not completely understood. And this has to do with this technical assumption. But so the short answer is that there exists a free monatomic version of the category for which you have causal duality exchanging BE and the free monatomic version, and from which this version is obtained by killing the polynomials on one side.
The technical assumption on W or on the realization H?
On the so this is a technical assumption on the realization H, and this has to do with the construction of this free monatomic version. So in fact, there is a work by Makizumi and Hogenkamp where they have announced that this technical assumption is always true, but their work is not published, so we cannot really use it. So we have a baby version of this. So we have some explicit condition on which this technical assumption, well, which imply this property that we need. If someday the paper is completed, then we can remove our condition. Yes, we expect that the condition can be removed, but for now, using only what is in the literature, we have to make some small technical assumptions. Yes?
So can you say something about this BW, because it's not defined intrinsically for the category, so like tilting and those delta nabla modules are in there
well, so these objects B, they are the decomposable objects in the category we started with, in the Elias-Williamson category. And the other ones, so these they really live in this additive category. The other ones they live in the triangulated category. And So these objects, in a sense, they are. You can make.
Yeah, but it's a standard costandard, that's very natural. And then tiltings are those that have filtrations by them.
Yes, so these objects are, in a sense, the pure objects. So the pure objects. So there is no notion of weight, which is similar to the notion of weight for perverse sheaves. You can make sense of this, and then these objects are the indecomposable pure objects of weight 0. So you can characterize them intrinsically in the triangulated category.
For example,
in terms of vanishing of certain hum from delta to these objects, from these objects to nablas. Yes, there is a characterization in terms of weights.
So it may be helpful to say that in characteristic 0 they would be simple.
Is that
so no, that's essentially true. Well, so, in fact, this is true when so this has not much to do with the characteristic of the field, but rather whether the realization corresponds to a reflection faithful representation. So in particular, so in the setting where we can describe the theory in terms of Zergel bimodules and where the Zergel's conjecture or Elias-Williamson theorem hold, then these will be indeed the simple objects in the heart of the T-structure. And in general, they might not be, well, they might be in the heart but not simple, or they might even not be in the heart in general.
I would be curious, sort of, in a way, combined question. Yeah, I mean here we could expect also to have a sort of parabolic singular duality.
Yes.
And then we would love to be one-side representations of a reductive group principal block, and the other side tilting parity sheaves on the.
Yes. So that's in fact the first version that that was in our initial motivation for this construction. So in the case of in one case related to geometry, we did construct some parabolic version of this, which indeed relates tilting things related to tilting representations and something related to parity sheaves on a fine flag variety. And in fact, our motivation for constructing this in this setting was that we knew that these tilting objects, they were computing things. Some combinatorial data related to tilting representations in the principal block. So this is something that we wanted to consider, we wanted to compute, and but we didn't know how to say anything about the combinatorics of these tilting objects. And it's exactly by constructing this causal duality that we were able to relate these combinatorics to the P-canonical basis. So that was the first motivation for this construction.
Sorry, I'm a little curious why this kind of involution that means categorifications.
I'm sorry?
Why this kind of involution and that means some categorification?
I don't know. It's just that there was already this categorification given by the additional causal duality, and for some reason we wanted to generalize this. But
no, isn't the answer that sort of if you have I don't know, delta flag of the T, it's given by the H polynomial, and if you have a nabla flag of the B, it's given by the H tilde polynomial or something like this.
yes. Yes.
Maybe this is something I should know, but I'll ask anyway. So BE is an algebra object, right? It's monoidal.
So
E itself.
the category BE.
Right.
Yeah, it's a monoidal category. Yes.
Okay, so you can consider it as a regular bimodule, and now you have a right module and a left module. Are they related? I mean, can you?
Well, so in fact, there is this.
Is there a way of building a resolution of the regular bimodule or something like that? So there is this version of causal duality that involves the
bi-equivalent category and the free monotomic category. And this version is an equivalence of monoidal categories. So it's monoidal. And this equivalence here is an equivalence of module categories. But on one side, there is the BE category that acts, and the other one, on the other side, there is the free monotomic version. But I mean, each of these categories has an action on one side by the bi-equivalent category, and action on the other side by the free monotomic version, and they are exchanged by this construction and the causal duality at the monoidal level. So I don't know if this answers your question, but
It was very helpful anyway. And I think so.
If there is no further question, let's thank Simon again.